Apparently you can see and hear me, but I can't actually really see and hear you. So I am going to go ahead and give this talk kind of open loop and hope to be interesting. And I hope later on maybe we can find a way to do questions or something. So I work in robotics and machine learning and reasoning. And fundamentally, my goal in research is to figure out what are the computational mechanisms that we would need in order to make a really general purpose intelligent robot. So I'm not trying to make a robot to solve a particular problem, but in some sense, I'm trying to understand the fundamentals of AI and how they apply to robots. So one of the things that's really important to me is domain variability. So one of the things I like to think about is, what if I wanted a robot to be able to go to anybody's house in the whole world and make tea? So imagine that you had to do that. You would know that there's some way to make water hot and some place where they keep leaves of some sort that they put in the hot water and so on. And if you went to somebody's house, you could eventually figure out probably how to make some tea. So what would the robot have to know? So I want the robot to be able to handle a wide variety of domains and really also to be able to do tasks, to be really general in what it can do in the world. So the way I think about this problem is I think about myself being a robot factory. So I should say, inside AI and robotics right now, there's a lot of argument about how it is that we should make robots that can do all those things. So I like to think of my problem like this. I like to think of my problem that I have a factory, and I'm going to make these robots that I put out into the world. Let's say they're household robots. So one's going to go to your house, and one's going to go to somebody else's house. And my problem when I'm making these robots is thinking about, I'm just really worried about the software, thinking about the program that I put inside the robot that goes to everybody's house. So it's got to be one program that goes to everybody's house. And the way I want to think about this is that I'm looking for a program. It doesn't really matter too much. Don't worry about the math stuff here if it doesn't make sense, but the intuition should be fine, which is I want to find a program to put in the robot's head. And I want that program to work well in a wide variety of houses. And so the way I want to think about that is that the program that I put in the robot's head should work well on average over the distribution of houses or problems or domains that it has to go to and work in. So if you came to me and you specified a probability distribution over possible domains, and you said, Leslie, I need a robot that will vacuum this one room in this one house, then there would be very little variation in the domain, and I would know exactly what program to give you, right? The program to vacuum in that house. But if you said I need a robot to drive a car down a road, then I could work on that. Or if you said I want a general purpose intelligent robot, then I could also work on that. And in every case, I have to think about the variety of domains that the robot would have to go to and work in. So one of the things that's good about this view is that it kind of means that we don't have to argue about whether the robots have to do machine learning or not, for instance, because the more variability there is in the possible worlds that they'll have to go to, the more they'll have to learn about the world that they found themselves in. So it's kind of good. It's kind of good at the mathematical level. It means that we understand what our job is. But it's also kind of bad because what's hard now is the job of the engineer. What's hard is my job in the robot factory of you come and tell me about all the worlds that you want the robots to work in, and I have to figure out the best program to put in the robot's head. So that's a hard problem, and that's what I spend a lot of time thinking about. So one thing that's sort of interesting, one way to think about what's going on is, again, we might have a very specific problem or a very general problem. And we might also, me, the engineer, the person writing the code, we might have some uncertainty. We can think about the uncertainty of that I have about the world that the robot's going to go to. So there's robots for simple jobs, robots for complicated jobs. I know what's going on. I don't really know what's going on. And so most engineering kind of, focuses in this corner. It's like, well, there's a simple problem I need to do. Not necessarily simple, but narrow. And I know what it is, and I just have to design a system that works well in that problem. Also, there, I can think about cases where I want the robot to be very general, but I know in advance what it has to do. Problems where I don't really know what the robot has to do, it's going to have to figure it out on its own. And this kind of upper right-hand corner, which is what I'm really aiming at, which is, well, I'm going to have to do a lot of different things, but I don't really know much about them in advance. So how do we think about making a good policy? And one of the things that's interesting is that the way we think about making robot programs is actually probably fairly different from what at least non-engineers think we do. So if you did Lego Mindstorms ever in your life, or Turtle graphics or something, you programmed a robot by telling it to like move forward and then move forward and then turn left and then turn left and then take a picture and then move forward. But that's not how we program robots. It's certainly not a way that you could program robots to work in really a wide variety of domains. So instead, we really think about problems in a different way. We think that the engineer has to do some work, generally speaking, of specifying something about the possible set of solutions that there might be to the problem. And then a computer does a lot of work really for us, doing optimization or running certain kinds of machine learning algorithms or parameter tuning. And so when we think about designing robots, robot software and the work that we have to do in the factory, we have to pick a kind of a solution class where humans can give good leverage, can help with the design process, where the computational problem is not so hard, so the optimization is easy, and also we hope that the thing will generalize well to a broad variety of problems. So we can think about different ways of finding strategies in different parts of the space. So as I said before, this is kind of the classical engineering strategy. And I don't know if you've seen it, there are these great movies of the Boston Dynamics robots. This is Atlas doing parkour, and it is super awesome. But it is a program for this robot to do this thing in this moment where they knew exactly what it had to do. So that's the kind of the classic engineering paradigm. There's some other stuff that you may have seen in the news. There's a cool, demo. You can see a video of a robot that's manipulating a Rubik's Cube. And what's fascinating about that is that it did it using machine learning. But it did it using machine learning in simulation, and it was on the order of, now I've forgotten, but like 80 years of simulated manipulation time. So that's a kind of learning that you can stand to do in the factory, maybe, right? You could do it, you can spend that computation time, and it's kind of like spending engineering time, because what came out of it in the end was this robot that could only do one very specific thing, which is manipulate this particular cube. So those are kind of two really different engineering strategies for arriving at a similar kind of capability. So this is just an illustration of an interesting thing. So probably a lot of you have heard about reinforcement learning. It's in the news all the time. And what's interesting is reinforcement learning was originally invented to be a model of how like an animal or a human might learn during their lifetime from interactions with things in the world. But what it's turned into, mostly what it gets used for a lot of the time, is actually a kind of a strategy for learning, for kind of computing in your head, imagining what it would be like to manipulate that cube, let's say. But it takes so long and requires so much computation, it wouldn't work online. It wouldn't work on the actual robot. There's no way you could get that much experience for the robot. And so you do it in simulation offline, and that gives you a strategy that you can execute online. Okay, so we looked at this little corner in the left. One thing that's been going on is machine learning has been helping us solve problems of a variety of kinds, but still mostly, so AlphaZero is a strategy that learned to play chess and Go and so on. And in these cases, what's interesting is that it still falls into the category of the engineers knew what problem they were trying to solve. There was no uncertainty about the rules of the game of Go, for instance. We know the domain very well. We use some machine learning type techniques to help arrive at a better strategy for playing Go or play chess. So some work that I have done before, and I'm going to talk about a little bit, is something called Hierarchical Planning in the Now. It's a system we've been working on for a long time that tries to push a robot toward operating in environments more generally. And so instead of doing reinforcement learning in the factory, right? So in the reinforcement learning in the factory view sort of says, we're going to do a ton of work offline. We're going to think and think and think and think offline. And we're going to come up with a kind of well, in their usual case, a neural network that just knows what to do at every step. An alternative view is that we build a system that kind of thinks online. It tries to perceive the state of the world. It tries to plan what to do. It takes some control actions, and it operates in this loop of looking at the world and making plans and thinking about what to do. So there are two very different strategies for building systems that interact with the world. And one of the things that's interesting is what you have to specify in the different cases. What I want to do here is not get into that in great detail, but think about how, if I was going to make a robot that does its own reasoning online about problems to solve, how should it model the world that it's going to interact with? So models are really important. The basic model, you might say, for a robot to manipulate things in the world, pick them up and put them down, rearrange your cupboards. You might say, well, okay, my robot has a bunch of joints and each of those joints has a motor and I can apply torques with those motors. So my action space might be the, kind of vectors of motor torques that I send maybe, I don't know, 100 times a second. So the horizon is really long. That is to say, the number of steps in some sense that the robot would have to take to arrive at a goal. And it is really, really hard to find long trajectories in that high dimensional space, and to think about how it is that by moving my joints, I can give a talk, right? So I'm doing that. I'm moving muscles in my tongue and my hands and so on, and I'm giving a talk. But really the action space, the level at which I'm thinking about giving this talk, it better not be at the level of activating my tongue muscles. So how can I think about other levels of abstraction? So I think about instead reasoning at a higher level of abstraction where we think about objects and we think about what are the operations that we can perform on an object. And one general message that's really important to us in general and is important in engineering and science in all kinds of ways is the utility of models or abstractions. And for us, we make an abstraction, right? So I think about what words I'm saying or what concepts I'm trying to convey instead of tongue muscles. What makes the abstraction useful? One thing is it should make my computational problem easier, right? That's the reason we make an abstraction usually, is because it's easier to plan or reason at this abstract level. It will almost always make the solution quality worse. So it will almost always be the case that by kind of abstracting some details away, we lose the opportunity to do some very careful, very fine-grained thing. It should also be not too hard to kind of implement and solve the problems you care about. I'm going to show you a picture of a kind of abstraction and just talk about it for a minute. So let's focus on the problem, and I'll show you a robot that does this in a minute. Let's focus on the problem of just interacting with rigid objects. So imagine I have a robot with a hand and it can pick objects up and put them down, basically. Let's imagine that's all I can do. So we could try to think about how to control the robot. And usually when people think about control theory or something, they imagine that you can look at this, I hope you can see my mouse, I don't know, but in the upper left corner of this figure, you can imagine there's some kind of big state space, and there's a submanifold, some kind of subspace. So you might imagine that when, let's say, I'm moving my arms around in space, there's a whole bunch of dimensions of the state of my office that are the same. The books aren't moving, my coffee's on the table, these things aren't changing, but what's changing is my configuration of my joints. And so I'm moving around in that one little sheet. But now, if I wanted to pick up something, maybe I want to pick up my coffee cup, how does that go? Well, I can change. It turns out I can change the position of the coffee cup. I can't change, though, the position of the coffee cup by looking at it, right? So now imagine that this purple manifold kind of represents the position of the coffee cup, or me and the coffee cup, actually. So what has to happen in order for me to pick up the coffee cup and move it around is that I have to work my way along my green free space manifold until I'm at a point, that dot, that Q prime, where actually my hand is, let's say, on the coffee cup. And now I'm in a different mode. I like get to move on a different sheet, a different submanifold of the space. I can move the coffee cup around. So that's pretty cool. And then if I want to get rid of the coffee cup, I have to go somewhere else and put it back down. And that's going to be a different sheet. So what's interesting about this abstraction, this way of thinking, is that it models the idea that I can make continuous changes in the state space, and I can make discrete changes. And in those discrete changes, I'm actually changing the way the world works in a sense. I'm changing how my muscles affect the state of the world. Once I'm grasping the cup, it's like I'm a new robot. So this is a cool abstraction. It lets us solve a bunch of problems. I can show you in simulation the robot doing a bunch of things, and it's all sort of entertaining. But let's look at an actual robot. So this robot has some extra kind of conceptual stuff in it. It does hierarchical planning and replanning, which is sort of important. Okay, so I'm going to show you now a robot video, and I'll talk about it while it plays. But I have to always give a little speech before I show this video. Any particular thing that this robot does, any of you guys with, I don't know, a few weeks of trial and error could probably program the robot to do. So the fact that it can do anything that any given thing that it does is not so interesting. But what is interesting is that the same code, almost exactly the same code, not precisely the same code, but basically the same code, is going to be solving all these problems. And that's what's good. It's also important to know that the robot doesn't know where the things are in the world when it starts out. So it's using its own perception to see the objects and figure out where they are and where it is relative to them. It's also important to know that the robot is kind of sloppy. It's a nice, safe robot, but when you command it to go to a particular place, it doesn't go there exactly reliably. Okay, so here's a case where we told the robot to put the blue box where that soup can was. And it looked and saw the soup can was in the way, so it figured out it had to get the soup can and move it. Here, it wants to get the green block on the corner. And the green block is too big to pick up, so it has to push it. It figured that out. It figured out it had to move the orange thing out of the way. It also knows its pushing is really kind of unreliable, so it looks after it pushes to see if the object went where it was supposed to. Here, we asked the robot to go out of the lab, but there were these chairs in the way. It checked to be sure that its space was free before it went, and it saw the chairs. And here, it went out of the lab, but it just brought one of the chairs with it. So we never told it to do that, but it did that. Here it's trying to find an oil bottle that's full and put it on the other table, so it can figure out that it needs to pick the oil bottles up and see how full they are. This is doing a random thing with a simulated engine. So there was some idea that it was supposed to pour oil into an engine. We never got to the point of pouring. And now it's running on a different robot and even running on a different robot in Singapore. Okay, so this was all pretty good and pretty fun. And I actually did a lot of the programming on here, which was also fun because despite being like an old professor person, I still really like hacking code and playing with the robot. So that was fun, but it was completely hand engineered. And so then the question is, well, what if you want to make the burden on the engineer easier? And what if you want the robot to be able to really learn new things when it goes into somebody's house? So now we can start to think about what happens when we're uncertain about where the people making the robot don't know exactly what it's going to need to do. And so one strategy is just have the robot do all of its learning in the world. But I always worry that if a household robot came and it didn't know anything at all and it had to learn everything about the world, I wouldn't want it to be doing that learning in my kitchen. So what I want to do is now just talk a little bit. I have 5 minutes. Talk a little bit about work we're doing right now, which tries to take the kind of underlying structures that we use to make that robot that did all the stuff that I just showed you and add more learning capability to it so it can learn new things. And I'm going to have to blast through some slides here, but I'll try to give you the basic idea. So here we're assuming that the robot, maybe it's used basic reinforcement learning, which works pretty well to learn a new basic skill. And we want to figure out, so let's say it's learned how to pour, just basic pouring. But we need to figure out how can it use what it learned about pouring? How can it figure out how to integrate that with the rest of what it knows about what's going on in the world? And I'm going to skip the details. We use some super cool machine learning methods that are conscious of their own uncertainty about what's going on in the world. That lets us actually learn when the pouring skill is going to work out, right? So we're trying to learn what relationship has to be true between the thing that I'm pouring out of and into, how, what should their spatial relationship be? How does it depend on the sizes of the things? How fast should I tip, and so on. And so we can do some learning, and it works pretty well. I want to show you this because now we used in the real robot, we tried to learn about how well the pouring and scooping works. And just to show you that machine learning on an actual robot with actual like chickpeas, it's like a lot of work. We had to pick a lot of beans up off the floor in order to get this to work. But eventually, we were able to learn new things and integrate it with its ability to already do stuff. So here's the robot executing now some of the skills that it learned, and it's put them in its general purpose planner. So we can put these objects anywhere on the table. We can tell it a weird goal. Like here we said, oh, you should serve some stuff by making sure that in the end state, the red bowl is on that tray and there's stuff in the bowl. Here it's, we told it that it should end up with the small bowl on top of the purple box and stuff in it. And the other thing you see is that it's moving other objects out of the way as it needs to. Oh, this is a nice example. So here it needed to pour stuff into the red bowl, but the red bowl was too far over on the other side of the table. So it figured out on its own that it should push the red bowl over. And there again, it moves the red bowl into a place that's accessible. So this kind of general reasoning about accessibility and geometry and what's in the way, it can use it even though now it's using it for a different purpose, which is this ability to pour stuff into bowls. Okay, so this is a little bit of a joke slide. The purple slide, the basic slide, is something that I used to conclude a talk that I gave in 1997, which is like forever ago, but I can amend it a little bit for now. So I would say that there's been a lot of progress in algorithms for supervised and reinforcement learning. That's true. And now there's really been like a ton of progress. But it still doesn't really give us the answers to solving the problem of making general purpose intelligent systems. And I think still that we need human insight really in the form of algorithmic and structural biases, ways of structuring the problem that scaffold learning and help the learning be more efficient. So I've done this work with a bunch of students and colleagues, and just for 1 minute, I'll let you watch the robot make mistakes, because that's actually always more fun than watching the robot do the actual stuff it's supposed to do. All right, so if we were live and it were a normal world and time, you could ask questions, but with that, I'll say thanks much for your attention, and I hope you enjoy the rest of the conference.